Good afternoon, ladies and gentlemen. My name is Tamas Szekely. I'm from Hungary. I'm working from Danfoss as Business Development Manager. In the first presentation, we heard about the efficiency of the district heating system, at least in the primary side. But we can contribute to the energy efficiency on the secondary side as well to be even more competitive and even more efficient total district heating system. What you can see on the picture, it is what's called tsunami. The tsunami is all the time terrible. A lot of damages, a lot of death. What about the connection between this tsunami and the mechanical engineering? I have to tell you, we have also tsunami, but this tsunami is inside the pipe and not visible. Therefore, very few of us know about the problem with the overflow. In this presentation today, I would like to talk a little bit about this phenomenon and about the problem surrounding the overflow. When we are talking about the energy demand, we can see the demand depends on the insulation of the building, the windows, how much heat we will lose on the chimney, etc. It's quite obvious. Everybody knows about it. If we talk about the energy saving potential, we mention many different things. For example, use thermostatic radiator valve, condensation boiler, use solar energy, and stuff like this. But I have never seen such picture what you can see on the screen, the energy saving potential with hydronic balancing. I would like to point out today on it. I will do it through on a building which is a realistic building. It can be maybe here in Serbia, a 5-story building, normal, conventional 2-pipe heating system with single or twin connected radiators. The average heat demand of the radiators around 1.5 kilowatt with 20-degree delta T. It could be around 65 liter per hour flow rate. This is not a so big building, around 100 meter long, and we use radiator valves and lock shield valve in the return pipe. Very important, how do we design the system? In my calculation, I used 100-200 Pascal per meter nominal pressure drop for pipe sizing, which will be strongly affect of the overflow phenomenon. In our case, I used 5 kilopascal pressure drop on the heat source. It can be boiler or it can be heat exchanger. Normally, the pressure drop on heat exchangers in a district heating substation is more than 5 kilopascal, but I tried to calculate a little bit more safety side to show you the realistic figures. We have all the time eternal question. To use a well-known manual balancing to ensure the water distribution in the system, or use the new technology, automatic balancing valve in our 2-pipe heating system. I will compare these two solutions in the next slides. To show the realistic figures, we have to investigate the system a little bit closer. You can see the graph of the system on the screen. The details of the system, as I mentioned, not changed in this slide, only I have to add a few more details, like the delta P demand of the control valve on the radiator is 3 kilopascal, the pressure drop on the radiator 1 kilopascal, and I use manual balancing valves on the bottom of the risers, which needs minimum 3 kilopascal for proper measurement and set the right flow rate on the different risers. If we add the total pressure drops of the system together, we can get the pump head, how much kilopascal we need for pumping. It's quite simple and easy. This is the engineering. But we cannot stop in that point because we have to know what is the pressure diagram of our system. Here, let's see what is the real pressure graph. We have the riser, we have pressure demand of the riser of the control valve radiator, and with the gray you can see the extra pressure demand for the pipe pressure drop. And on the bottom of the riser, you can see a pink area. This is the pressure demand of the manual balancing valve, what you can see in the bottom of the riser. We have to ensure this minimum delta P for the riser in the bottom of all risers. And the distribution pipeline pressure drop we have also to add to the total picture. And now we see with the extra manual balancing valve in front of the pump, what is the pump demand, pump head demand. We can see clearly we have much bigger available pressure in the beginning of the system compared to the end. Therefore, we have to use the manual balancing valve, in this application at least, to reduce the overpressure in the bottom of the riser and also the overpressure in front of the radiators with the presetting valves. In this case, we can say this system is working properly when we have 100% flow rate in the coldest outdoor temperature and without internal heat gain. Can we satisfied with it? No, because this is only a few hours in a year in the total season. Therefore, we have to investigate the system in partial load condition as well. Let's see what partial load condition, namely 50%. In reality, the partial load condition is even less than 50%. In reality is 30-40%, but for easy calculation, I used this 50%. You can see with this gray line what is the available pressure on the distribution line and on the riser during the partial load condition. Because the pressure drop due to the lower flow rate through the pipes, the pressure drop will be smaller. Therefore, the available pressure on the end of the riser will be dramatically increased, and not only to the end of the riser, then the top of the riser even more increased. Here, instead of the originally preset 4 kilopascal, we will have 37 kilopascal. This is a huge overpressure in that point. What is the consequence of it? If we easily calculate what is the overflow through on this radiator, matter of fact, the worst located radiator, it is more than 3 times more water will flow through on this radiator. It's definitely a huge problem. Okay, let's see what will happen if we use pressure differential controller in the bottom of the riser. In this case, if we presume the same system, exactly the same system, lengths and equipments, expect this different delta P controller in the bottom of the riser. We can calculate the pump head. You can see here a little bit bigger pump head we need. Just because we have this delta P controller, and for proper operation this delta P controller, we need minimum 10 kilopascal pressure drop on it, and with this we can ensure right constant delta P control for the riser. Let's check how we'll modify the pressure diagram of the system with usage of delta P controller. The basic situation exactly the same. We have a commission system with pressure drops in different places, but now if we use delta P controller in the bottom of the riser, we don't have to use manual balancing because this delta P controller will automatically set by itself and reduce the unnecessary pressure what we can experience in the beginning of the distribution pipeline. If we use delta P controller, definitely we will have overpressure on the distribution pipeline, but the delta P controller will simply remove it, and now we can see the unnecessary available pressure will be arise only on the risers. What is the overflow here? Now we can see the originally 4 kilopascal overpressure increased up to 6.25 only. It's not so big. Of course, the pressure is bigger than we expected, so that will be some overflow. But this overflow is only 25% compared to the previous system when we had 3 times more flow rate. So this is the situation in the far end point of the system. But to know more about the system, we have to check what is the seasonal overflow in the total system. Because the overflow depends on the location of the thermostatic, the radiator valve, the terminal unit in the system. Depends on the incident factor, how many hours we're working in different load profile, 75, 50, 25, or 100% load. To this calculation, I use the Blue Angel method, what is most often used by pump producers companies to show what is the seasonal average incidence factor. You can see here, for example, for 25% load profile, we have the longest in the whole season. And we have to take into consideration in our calculation. I used my own overflow calculator, and I found the overflow in case of usage of manual balancing valve, the seasonal overflow will be more than 21%. If we use automatic balancing valve in the bottom of the riser at the 5 storage building, that will be 18% overflow only. We can see this is a huge difference. And of course, this overflow will take effect on the energy efficiency. Why? Because we know very well the hydraulic-based heating cooling system energy efficiency depends on the circulated water quantity. If we circulate more water, in this case, we will have more energy consumption. I would say overconsumption compared to the ideal situation. What could be this, where from this overconsumption come? 3 very important points where we can line up what kind of overconsumption can appear. The first one is the electronic consumption of the pump. If we circulate more water, definitely we will have higher energy bill on the pump cost. Efficiency of the boiler. If we have overflow, definitely we will have lower pressure, temperature drop on the radiator. That means the return temperature will increase. If the return temperature is higher, we can use less efficiency of the chiller, or of the boiler, or the substation. If it's thinking about the cogeneration and the district heating system, we know very well if the return temperature from the district heating system is too high, we cannot utilize the maximum efficiency of the turbines of the electricity production. Let's see them one by one. The first one is the energy saving on the pump. You can see on the picture the comparison of the energy consumption in case of usage of constant delta P control on the pump, and with orange, the energy consumption of the proportional pump control. If we have manual balance system, we must to use constant delta P control on the pump, otherwise could be some suffering terminal units because of underflow. In case of automatic balancing valve, we can use proportional control, which consume much less energy. If we take into consideration these 2 effects, we can see clearly how much more energy we use with manual balancing valve with constant delta P control pump. The next effect is the saving on the boiler, for example, if you're talking about the boiler system. Especially if you use condensation boiler, it's very, very sensitive about the return temperature. You can see on this chart how change the efficiency of the boiler based on the return temperature. As I mentioned, we have overflow in the system, smaller delta T, higher return temperature, lower boiler energy efficiency. And the last one, but not least, we have to mention the overflow effect on the room temperature control. If we have overflow in the system, we have higher room temperature oscillation, because this overflow will ensure more emission of the heating radiators. In this case, the system will be overheated, and it will be most often open the window and leave out the energy through the window. We know very well, in case of 1 degree higher room temperature, requires around 5–6% higher energy from the heating plant. If we add these 3 parts together, we can get the characteristic of the overconsumption based on the overflow in the system. If you remember, I talk about 80% overflow around in manual balance system. You can see, based on the calculation, it will result around 10% over energy consumption. Let's check how fit the energy saving calculation on a theoretical level compared to the reality. To that, I would like to show you a case study from Poland. We had 2 buildings which was not properly balanced, but the heat measurement was done in year 2000 and 2001. In the summer 2001, we renovated the 2 buildings. One of them was equipped with manual balancing valve and properly balanced, commissioned. And the other building was equipped with automatic balancing valve, delta P controller, and also commissioned. After a year, we measured what was the energy consumption difference before the renovation and after the renovation. We experienced the energy saving potential based on usage of automatic balancing is huge, because the saving difference after the renovation was 11%. That means if we don't use any balancing in the system, probably we have around 14% more energy usage. If we use automatic balancing, the energy saving potential 25%. The difference of them is 11%. So very close to the previously shown energy saving potential in theoretical level. It is proved in reality based on the real measurement. So how can we help on the secondary side to improve the efficiency of the district heating system? Please use automatic balancing for the 2-pipe radiator heating system. There are few further benefits if you use this solution. Not only the energy saving, then we can ensure better comfort for the users, less complaint to the maintenance people, and longer lifetime whole the working period of the system. And of course, there's some others like environment friendliness and stuff like this, but because lack of time, I wouldn't like to talk about these additional savings. Thank you very much for your attention. Questions?